My name is Fabian Retkowski, and this presentation is about advanced value-based reinforcement learning for sequence-to-sequence architectures. First, let me motivate the research with an example from the area of dialogue systems. On the left, you can see a model trained on a movie dialogue corpus. When we input questions like, what are you doing or how are you, all top-ranked answers of the model are highly generic, dull, and non-engaging, such as I don't know or I'm fine. The reason is to find in the maximum likelihood objective, which favors high-frequency phrases. However, this is in sharp contrast to the real-world goal and from what would you expect from a dialogue system. You want interesting, diverse, and informative responses. We identified two approaches how reinforcement learning is currently applied for dialogue systems. If you have a restricted domain, like movie or restaurant booking, often task-based dialogue systems, you can separate the components and use templates or dialogue acts as actions. In this case, you have a manageable number of actions, which allows you to learn from scratch and apply either policy gradient methods or DQN. In contrast, there are sequence-to-sequence networks. However, here we deal directly with the vocabulary, which makes it high-dimensional. The application of reinforcement learning is currently very restricted. It's limited to fine-tuning, and this is also why we only have limited performance gains. In addition, we are restricted to policy gradient methods because they have softmax outputs, and those can be easily pre-trained using supervised learning. However, in the long term, we may want to apply reinforcement learning to sequence beyond the limited use case of fine-tuning. And with this work, we want to contribute to reach this goal. It's a rather foundational research, and the research questions we came up with are, is it possible to train a sequence-to-sequence network with value-based reinforcement learning in theory? If yes, to which vocabulary it can scale, and what helps the model to scale? In the end, we want to have a framework for training such a model. We want to have valuable insights and provide a baseline for future work. Here we see different reinforcement learning algorithms evaluated on Atari games by Hessel et al. At the very bottom, we can see very basic DQN and A3C not able to reach human levels. These are variants of DQN with extensions like prioritized experience replay or dueling nets. And then we have a state-of-the-art setup, which is called Rainbow DQN, and it is able to perform this well by combining 6 improvements. These improvements are listed on the left, for example, multi-step learning and distributional reinforcement learning. And the stellar performance of Rainbow in several domains motivated us to transfer the Rainbow setup to the sequence-to-sequence architecture. Now I will cast the sequence-to-sequence problem to a reinforcement learning problem. In the context of this work, the action space A is the vocabulary space. So at each time step T, the decoder of the sequence-to-sequence model chooses the next action AT, which is the token in a sequence of actions. The state ST at a specific time step T needs all the input data that is required to produce the next action AT. Since the decoder generates its output depending on the previous hidden states and the previously chosen action, this tuple might be used as the state. However, the hidden state representation is not static, but highly dynamic, as it is learned during the training process. So it is not suitable to be replayed in later phases of training. Instead, we may use the input sentence and all previous actions as the state. With this information, it is possible to reproduce the hidden states and eventually output the action. The reward function can be any user-defined function, but for simplification and for comparison, we have chosen bleu and rouge as exemplary rewards. For two reasons: to focus on the feasibility of transferring DQN to sequence models, and second, this way we have a kind of a ground truth we can compare to a fully supervised baseline model with cross-entropy loss. This is the basic DQN algorithm, and we will go through it step by step while introducing methodological changes from the paper on the way. The first step is to collect data, and for this we have a data set at hand from which we can sample a batch. And then we can use the source to input it in our rainbow sequence-to-sequence network and generate a new sample. In the next step, we can obtain the reward using the sample. And as I said, the reward can be any function like bleu, rouge, human feedback, or mutual information. In our case, it is bleu and rouge, so we also need the target to calculate the reward. Our experience is then to be added to the replay buffer. However, the classic replay buffer, as seen on the left, usually only stores single transitions, which is a tuple of a single state, the action, the next state, and the reward. When we apply our definition of state and action to this setup, then the state is the input data x and the output tokens from time step 1 to t-1. The action is yt, and the next state is x and y from time step 1 to t. Note that there is quite some redundancy, and this transition also implicitly includes all previous transitions. And this motivated us to summarize it by storing the whole input x, the whole output data y, and the reward. And this also allows us to replay the whole episode then. One of the DQN extensions that is heavily affected by this decision is prioritized experience replay. Once again, on the left is the classic version. The basic idea is to use the last encountered error as a weight or priority to sample such transitions. However, in the paper, we use whole episodes for the replay buffer, so a sequence of transitions and errors which requires us to aggregate these errors in some way. And there are at least two ways which are averaging and summation. The next step is to sample a batch from the replay buffer and update our network. For replaying the episode, we have borrowed a method from fully supervised learning, which is teacher forcing. However, while the technique is the same, it's used differently. In supervised learning, we feed targets into the network, while for reinforcement learning, these are samples from the replay buffer and may also be completely wrong or suboptimal examples. And our network then outputs Q values, and together with the stored reward from the replay buffer, we can finally calculate our actual target and calculate the temporal difference error. Additionally, we can raise the question how to utilize demonstration data as we have some corpus data at hand. A simple way is to preload it into the replay buffer directly. The idea is to allocate a part of the replay buffer to the corpus data, and there we insert demonstration data with a reward of 1, which is the optimal reward. However, our demonstration data is excluded from the replacement strategy, and it's permanently stored. We evaluated different aspects of the model, which is the scalability, the effect of the extensions via an ablation study, and different ways to utilize demonstration data. For the presentation, I will focus on important and interesting aspects. For evaluation, we trained the models on the Cornell movie dialogue dataset and used bleu and rouge as evaluation metrics. While these wouldn't be used as metrics or rewards in practice for a dialogue system, it allows us to have a clean comparison with a fully supervised baseline model. We evaluated the scalability with 4 settings. For each, we doubled the vocabulary size. We can see that our model matches and even outperforms the fully supervised baseline model in 7 of 8 experiments. However, around a vocabulary size of 800, it seems to reach its limits of scalability. The models are quite similar. In more than 80%, all of these models output the same sequence. However, there are some examples, a few, where you can see the very different nature of learning. For example, when we input something like what time is it, the rouge model, the reinforcement learning rouge model, outputs what, why. And the targets in our data set are what and why. And why is that? Because what, why scores a higher combined reward than either of the targets. This shows once again how important it is to choose an adequate reward function. One interesting thing from the ablation study is that the most essential extension is multi-step learning. This is similar to the results as found by the original Rainbow paper. However, here it is much more essential. Why? Because we only get rewards at the end of the episode, and combined with the fact that our final action is always the end token. So all other tokens rely on bootstrapping only. Also very important is the prioritized experience replay, and also significant impact on performance and scalability has distributional reinforcement learning. However, it is highly sensitive to the number of quantiles. In the original paper, 33 quantiles was used. Here, however, 2 to 5 seems to be a reasonable choice. Yeah, and also the preloading of the experience replay buffer is very essential, presumably because it's it's used in conjunction with the prioritization. Although it's only a small part of the replay buffer, it has a huge effect. So conclusions. So we have shown that we can apply advanced value-based reinforcement learning methods to sequence-to-sequence architectures. Practically, it's still limited by scalability. However, we identified several components as essential, which are multi-step learning, prioritized experience replay, and distributional reinforcement learning. Also, the preloading of the replay buffer with corpus data. Also we provide a baseline for future improvements. So future work, while Rainbow is still considered to be a state-of-the-art setup, there have recently been some major improvements in the area of distributional reinforcement learning. Also, it could be helpful to switch to a distributed architecture with multiple agents. And there are also some approaches for dealing with high-dimensional action spaces, specifically like value penalty, amortized through learning, or action branching. And Yeah, and we could also explore different data representations like character level or byte level instead of word level actions. Maybe DQN is better at handling longer sequences instead of larger action spaces. Yeah, thank you so much for your attention. This is all for today.